Second part also is clear, right? Um, so let's go to the second question. This is very simple. Uh, Assuming the number of years a car will run is exponentially distributed with mean, and suppose Mr. Alok buys a car today, what is the probability it will run after 3 years? Right. So the lifetime of that whatever the car running is distributed with exponentially distributed with mean 8. What is the probability that it will run more than 3 years? After 3 years means it's more than 3 years. So it is very simple. Um, X is exponentially distributed. You remember exponential distribution is parameterized by only one parameter lambda, right? And it is related to mean by 1 over lambda. Mean is 1 over lambda. That's why lambda is 1 over 8, right? You are given this thing. Mean as 8. That's why lambda is 1 over 8. Now, what is the probability that x is greater than alpha for any exponential distribution, right? It is nothing but e power minus lambda times alpha. Okay, so just applying that, you get this e power minus lambda times 3. That is really e power minus 3 by 8. You have understood why I have written the first part, x greater than 3. That is coming from the exponential property of exponential distribution, right? Probability x greater than alpha is equal to e power minus lambda. Okay. Any questions on that? That's exponentially distributed, right? F small f, if you denote it as PDF, that is nothing but lambda e power minus lambda x. X goes from 0 to infinity. So let me put this simply, right? This is exponentially distributed, and lambda e power minus lambda times x, right? This is fx, small fx. Right now, probability that x is greater than some alpha is equal to e power minus lambda alpha. You can just integrate this to alpha to infinity and check it for yourselves. You should be able to get this. Okay. Cool. So yeah, that's all for the second question. And coming to third question, this is also very simple. Suppose the life length of two electronic devices have normal distribution, right? So Gaussian distribution. This is mean and this is sigma square, square of standard deviation. Okay. Similarly, this is mean and square of standard deviation. And you are given the phi. Phi is nothing but um, this phi is nothing but the how should I put it? I so phi they have defined it something like this: p of z less than or equal to z, and z is the standard normal. The standard normal is 0 mean 1 variance. So n of 0 comma 1. Okay. So they have given phi of 1 by 3 means probability that z less than or equal to 1 by 3. Okay. And z the distribution of Z is 0 mean univariate. Okay, so they are given many options, so we have to choose one. If the device is used for 45 hours, um, that means if it is already used for 45 hours, we need to check what is the lifespan more than 45 hours, right? So you need to ask what is the probability that X or whatever under distribution D1, D2 is greater than 45. Similarly, X greater than 42 under distribution D1 and D2. Whichever is larger, you have to choose that. Clear, right? The explanation of question and the notation. Okay. So go to solution. Yes. So we want X greater than 45. And so we'll see what is D1. D1 is mean 40 and variance 36. Right? So we are asking what is the probability X greater than 45 for D1 distribution. Right? So this is same thing written like this. So basically subtracting the mean from X, and you divide by sigma. Okay, and sigma is 6 here because variance is 36. This is greater than 5 by 6. Same thing, just that if I give this greater than is replaced by less than, that's why this is 1 minus. This becomes 1 minus of that. Okay, and this is 1 minus phi of 5 by 6. So one thing I wanted to highlight here is um, here z is nothing but your n of 0 comma 1, right? And given any x with n of mu comma sigma square, right? X minus mu by sigma will be distributed as z. Clear? So that is the reason I am able to replace this quantity by phi of 5 by 6. This phi of 5 by 6 is already given. Uh, right? Yeah, something like that. Okay. And similarly, same thing, you need to repeat the exercise for D2 distribution where mean is 45 and variance is 9, and you get this thing. D2 you end up getting 0.5 and even you get 0.2. So that's why you have to choose D2, right? Similarly, X greater than 42, just repeat the same calculation, right? And use the values given in the question of these, you will end up getting D2. So any questions on this calculation? You want me to go again on this D1 and D2 computation? Exactly, 5 values calculated numerically. We don't have any closed form things. So that's why they have been provided in the question. Okay. Yeah, you just it's a standard manipulation tricks. You just need to get used to it. Okay. The main thing is this. The main thing that I used here is this thing. When you subtract mean divide by the standard deviation, the resulting distribution will be normal. 0, 1, right? Mm, and let's go to another question. Right. So x1, x2, so on, xn are independently exponentially distributed random variables with parameters lambda 1 to lambda. Right. Now, what is the question is probability that x1 exceeds s by t, right? That is s plus t, given that x1 has already exceeded x, right? So we will see this. And what is the distribution of minimum of x1 to xn? Okay, so we'll see why they are. The same thing, same questions we are, same thing we are repeating. Uh, this is from this point to this point, it is by definition. Okay, we are just writing the definition of conditional probability. And this intersection is nothing but s plus t, right? And probability that x greater than alpha if it is exponentially random variable, I said e power, that is e power minus lambda alpha. Okay, so here e power minus lambda times s plus t divided by e power minus lambda s, you end up getting e power minus lambda t. But for lambda, for x1, lambda is nothing but lambda 1. Okay, so that's the first part. And this distribution for the minimum of x1 to xn, these are all IID random variables. Okay, so here the trick is if minimum of all this x1 to xn is greater than say some x, then all the random variables will be greater than x, because my least of all these n variables is larger than x. Okay, so that's why if z denotes the minimum, if minimum is greater than x, right, all random variables will be greater than x. Because of the independence, you are able to separate it out. Okay, and as I already said, probability x greater than or equal to x for exponential random variables is e power minus lambda 1 x. That's it. So this is again an exponential distribution because probability z greater than x is equal to e power minus some lambda hat x, where that lambda hat is sum of all the lambda x. Got it? Step right after taking the minimum. Okay. Uh, okay, this step, right? This. So uh, let's say minimum. Let's take only three numbers. Okay. So what I'm saying is, let's keep the three numbers says 1, 2, and 3. Okay, and minimum of 1, 2, and 3 is 1. Okay, if 1 is greater than or equal to 0.5, 2 is also greater than or equal to 0.5, and 3 is also greater than or equal to 0.5. That's what I meant here, right? If minimum, whichever it is, right? If that is greater than x, then all random variables should be greater than x. So is that argument clear? Okay. Because of independence, now this you are able to do individually, right? These are two events, right? Probability of A P is P of A times P of B because they are independent, right? This again comes from the straightforward exponential distribution, right? And that's it. Okay, so let's move to another question. Yeah, if x is a Poisson random variable with with the parameter lambda, then uh, which of the following is okay? Let's see, it's a bit lengthy, but that's okay. Okay, so this is the distribution of Poisson. The probability x taking a value of k. This is a discrete distribution. Remember, e power minus lambda, lambda power k by k factor. So this is by definition expectation, right? Because k is 0, it's you started from 1 to infinity. K is equal to 1 to infinity e power minus lambda, lambda power k by 1. Just take the e power minus lambda thing out and write k factorial as k times k minus 1, you end up getting this. Okay. And notice now, e power lambda is this expansion 1 plus lambda or 1 factorial lambda power over factorial and so on. Just multiply this by lambda on both the sides. This is precisely you have. So this entire expression, so whatever I'm highlighting here, right? This entire expression is equal to this thing. Okay, that is nothing but the lambda times e power lambda. Okay, so that's why it is your mean is lambda. Okay, clear? And yeah, we are given we want to find the moment generating function for this random variable. The moment generating function is nothing but expectation of e power tx. Just take the expectation again, right? And you remove this e power minus lambda outside, and right. So what you end up getting is take e power t and lambda into one term, right? So that's e power t lambda e power k by k factor. This is nothing but e power lambda times e power t. That's how it is e power lambda into e power t minus 1. That's it. Very okay. And yeah, so for variance it's a bit lengthy. So we'll compute the second moment first, and then from second moment we'll compute the variance by e of x square minus e of x whole square. Okay, so let's compute e of x square. E of x square by definition, just write down like this. Okay, so this is same as writing k is equal to 1 to infinity, right? K times k minus 1 factorial. So 1k has gone from this thing, right? So just write it like this, e power minus lambda times k times lambda per k by k minus 1 factorial. Okay, so just expand it out. Only the first term, k is equal to 1, will be lambda times e power minus lambda, and k is equal to 2. It will be this expansion. Okay, just expanded it out. K is equal to 1 separately and k is equal to 2. Okay. And yes, let's compute what is this summation now. Right? Here, add and subtract 1 and minus 1 from k. So k minus 1 times this k minus 1 factorial times lambda per k, again plus 1. Right? So one term, that will be lambda per k by k minus 1. So let's call this as term 1 and term 2, and let's see what they are. Okay, so again, this is from simple expansion. Equal lambda, you just get this, multiply by lambda. Again, you will get this thing. Okay. So the second term here is equal to this thing. Then lambda equal lambda minus lambda, because second term starts from this portion. Okay, k is equal to 2, lambda square by 1 factorial, lambda cube by 2 factorial, and so on. Okay. There's a typo here, it should be lambda cube. Okay, So let's see what is about with the first term. Right? The first term is this. We just expanded it out. I mean, just removing the k minus one thing here. Okay. So just consider the expansion of e per lambda. You get the same thing. Multiply with lambda. Again, multiply with lambda. You get this thing. Right. This is precisely is the second term. Right. Lambda square e per lambda. Okay. Substituting this one and this two here. Here, right? You will get this thing. So once you get this thing, you substitute into this. So basically, we add it and substitute it. So first term e per minus lambda times lambda, you had it here. I just carry it and e per minus lambda times these two terms, right? So you will get lambda plus lambda square because this thing gets cancels with this, and e per lambda times e per minus lambda is one, and you have lambda square plus lambda. So variance is e of x square minus e of x whole square. That is lambda plus lambda square minus lambda whole square. That is lambda. So this is the one distribution where mean and variance are same. Okay. So any questions in this calculation? It's just manipulation of the terms. I mean. If there are no questions, we can go to the next question. So anyways, I'll upload this file as well along with the PPT slide. Okay. But I mean, there is no questions, right? It's just a simple manipulation from the definition. And just expanding e per lambda and multiplying with lambda and lambda square appropriately as and when required. Okay, so let's move to another question. Yeah, so x is a random variable identified of two statements. So we want to know that e of x bar 2n is this thing, right? And e of x t, expectation of e power x t is e power sigma square t square by 2. And e of x for 2n plus 1 is 0 for n equal to 0. Okay. And the last one is not true. First three are true. So let's quickly see. So I'll prove this in the end, but assume that this is true for now. Expectation of exp of this sx is exp of s square sigma square by 2. Okay. Now the e of this x per 2n is you differentiate this thing 2n times. After differentiating, evaluate the term at s is equal to 0. That is nothing but e bar expectation of x per 2n. Okay. So I have computed this for n is equal to 1, and you should be able to see that uh, only first option satisfies it. If you want a generic solution, I think you have to differentiate it again and again and get this term, right? So just that it satisfies, just to see that it satisfies this thing with n is equal to 1, that should be given. Okay, so this is the general procedure. Okay, now the another question is expectation of odd powers of x is 0. Why is that the case? Is x is, if you expand this expectation, right, you get minus into plus infinity x per 2n plus 1 times fx of x. Now fx of x is 0 means sigma square. 0 means sigma square is an even function, and x bar some odd bar is an odd function, right? Even and odd, when you multiply, it's still an odd function, right? So negative side area and positive side area cancel out each other. That's why it is 0. Okay. So yeah. So let's prove this thing. Right? The first part I said, right here. This thing. Let's prove this thing. So we want to prove this e power sx is equal to exp of s square sigma square by 2. Expand by definition, just expand it out. E bar sx times exp. By the way, exp and e I denote the same. Minus this is x square by again. So what the trick here is to complete the squares. Okay. So we want to write this in the form of a Gaussian, right? So e power minus x square you have here from this thing, and sx is there, right? You multiply and divide it by 2 sigma square to sx, right? So 2 sigma square by 2 sigma square. So finally you get e power sx1. Okay. And now you add and subtract s square times sigma power 4. You add s square sigma power 4 and you subtract it. Okay, now you take it out this e power s square sigma square by 2. Okay. So basically you take it out exp of s square sigma power 4 divided by 2 sigma square. That will become your s square sigma square by 2. What you are left with is only this term. Okay. And this term you can simply expand as like this, right? Exp of minus x minus s sigma square whole square by 2 sigma square. This is nothing but your standard Gaussian thing with mean s times sigma square, right? And this integrates to 1. This whole thing integrates to 1. So you're left with this. Okay. Any question on that? Okay, and yeah. So an airline knows that only 5% of the people making a reservation on a certain flight will not show up. That means if 100 people book tickets, 95 will board the flight. So 5 will not make it. That's what that line meant. So consequently, their policy is to sell more tickets, right? So they sell 52 tickets if the flight can hold 50 passengers, right? Now assume that the passengers come to airport independent of each other. Now, what is the probability that every passenger who comes will find a seat? So you only have 50 seats, and there are 52 tickets have been sold. What is the probability that every passenger uh, who arrives at airport will find a seat? And remember, each passenger arrives at airport with a probability of 0.95, and he doesn't arrive at airport with the probability of 0.05. Okay, there's the question. The answer is very simple. Out of 52 passengers, up to 50 you can accommodate, right? So you don't have any problem if 50 people can come. At most 50, not more than 50. 51 comes up, you don't have accommodation, right? Very simply, simple. I mean, if none of them comes, it's great. I mean, Flight is empty, right? Trivial. If one comes, you can accommodate, and if two comes, you can accommodate, and if 50 comes also, you should be able to accommodate. That's the probability. It's a lengthy way of computing, but simple way is 1 minus probability that you cannot accommodate. You cannot accommodate only in two ways. One is like 51, out of 50 to 51 shows up, and out of 50 to 52 shows up. Okay, so that's it. That's the answer. Any questions on this? No? Okay, so let's move to the second question. Yeah, so a publisher claims that in the handbook published by them, misprint occurs with a probability of 0.0024 per page. What is the probability that a randomly chosen handbook of 300 pages, the third misprint will occur after examining 100 pages? That means in first 100 pages, you should have two misprints. Okay? So in 100 pages, you have only two misprints, right? So P is given 0.0024 and 1 minus P is 1 minus 0.0024. So uh, so if x1 you denote 1 as a misprint, right, and 0 as not a misprint. X is a Bernoulli random variable, and sum of all the Bernoulli random variables is binomial, follow the binomial distribution. Right? You want this to be 2 because it is binomial. Out of 100, 2 you want only 2, right? So that's why it is 100 choose to p square times 1 minus p, the remaining. Any question in this argument, especially this argument? Good question. So why we are taking sum of random variables? Hmm. Now you want to have a misprint, third misprint after examining the first 100 pages, right? So every 100 pages, say x1 to x100, the one denotes the page 1, right? And x1 denotes that a misprint is present or misprint is not present. Okay, similarly for second page, I am denoting x2 as Bernoulli random variable, where one denotes misprint is present and misprint is not present. And I want all the sums to be equal to 2. And this can 2 can occur anywhere, right? One x1 can take 1, x100 can take 1, or x2 can take 1, or x99 take 1. So how many all these possibilities exhausted are? It is simple. Out of 100, you choose 2, any 2, and allocate them 1 and 1. That's it. Clear? It's a useful trick. Um, so suppose the weight of the pumpkins is normally distributed with mean and standard deviation too. And I think it's a very straightforward question. It's a very simple question. Let's see. You're asked, you're given some random distribution following with mean 6 and standard deviation 2, and you want to know what is the probability that um, um, that pumpkins weigh at least 10 pounds. Right? What is the probability that what fraction of the pumpkins weigh at least 10 pounds? And what fraction weight between 4 and 8? Right? So very, it's very simple. If you have done the first second question, right, that D1 and D2, this is again. So W is normal distribution with 6 and sigma square. Remember, the question 2 is given as sigma. Okay, sometimes they give sigma square and sigma. Pay attention what they are saying. And you want W greater than 10. Same trick, subtract mean and do this thing, right? So that this part becomes standard normal, right? This is nothing but why this is 1 minus P of 2 is this part probability sum, let's say W minus 6 by 2 is greater than or equal to 2 is equal to 1 minus probability W minus 6 by 2 less than or equal to. So phi is defined if it is less than. Okay, so that's why it is 1 minus P of 2. Yes, so I'll just have written here. Okay. And the second question, so what is the probability that 4 is W is between 4 and 8? Same thing again, make it standardized. Subtract the mean and divide by standard deviation. So you have this thing, P of 1 minus P of minus. It's very easy. Okay, so let's move to the last question. This is very interesting. Uh, yeah, last question. This is very interesting. Okay, so let x be a Poisson random variable with parameter lambda. Identify the true statement. Okay, so you have a mean, right? Um, and what is being asked is if um, um, if your k and l, if your mean is between k and l, what can you say about probability x is equal to k and probability x is equal to l? And if your k and l lies to the left of the mean, what can you say about it? Right? Again, if your k and l lies right to the mean, what do you say about it? So all this is very easy to answer provided you know this. Okay? Just remember this figure. So this is, I mean, I'm drawing it as normal, but it is not exactly normal, but it does peak at some point. Okay, around mean, right? So uh, call this as this lambda, okay? And if your L and K lies to the left of the mean, right? Whenever K is less than L, probability that x taking K is less than probability x taking L. Whenever this K and L lies to the right of the this thing, right, lambda, and whenever K is less than L, probability x is equal to K is more than x is equal to L. But if say your L is here before lambda and K is after lambda, you cannot comment anything. Okay. So any questions? It's not symmetric, but it peaks around that point. That's why I told in the beginning. I have the figure is a bit misleading, but yeah, but it does have a peak there. It's not symmetric. Yes, yes, yes. That's true. And it happens around mean. I think lambda plus minus one or something. Okay, so I think that was an interesting question. Uh, so yeah, so let me stop recording.